We're going to talk a little bit about analytic geometry in this video. We've tried for most of our work to follow a synthetic approach to geometry. However, we did introduce some analytic postulates for distance metric and coordinate system for a line and for angle measure fairly early on. And we can also introduce coordinate systems for a plane and 3D space to allow us to apply some more analytic techniques. So that's how we're going to kind of get going on this chapter. Synthetic geometry is where we build up the geometry starting with the postulates, and where the postulates do not assume that we know the properties of real numbers. The only number of properties that we assume are the properties of whole numbers and perhaps rational numbers. If we take this to the extreme, we can actually eventually build up the properties of real numbers from the Euclidean geometry postulates. For example, if we started with David Hilbert's postulates for Euclidean geometry, we could build that up that way. In contrast, analytic geometry is where we base our postulates on the foundation of an understanding of the properties of the real numbers, for example, in Birkhoff's postulates. So recall that we've kind of taken a hybrid approach where we introduce postulates similar to Hilbert's, but we also include a few postulates similar to Birkhoff's, including postulates for distance and angle measure. In a similar manner, we're going to introduce postulates for area and volume in just a bit. And remember that our official list of postulates, definitions, and propositions is in the appendix to my textbook that we have here. Another feature of analytic geometry is the use of a coordinate system for a line, a number line, and a coordinate system for a plane, a Cartesian coordinate system. So recall that a coordinate system for a line is a bijective function c, which establishes a one-to-one correspondence from the set of points on any line to the set of real numbers, such that the distance is preserved. That is, the coordinate of b minus the coordinate of a, absolute value, is the distance from a to b. In a similar manner, we can use the coordinate systems from any pair of intersecting lines to create a coordinate system for a plane. We take a pair of intersecting lines with separate coordinate systems so that the coordinates of the intersection point are 0 in the coordinate systems for both lines. This intersection point is called the origin of the coordinate system for the plane, and the two lines are called axes. We designate one of the axes the first axis and the other the second axis. And we then obtain coordinates for any point in the plane as an ordered pair xy. To find the first coordinate, sometimes called the abscissa, we take a line through the point parallel to the second axis and look at the intersection of this line with the first axis. The coordinate of this intersection is the first coordinate of the point. Similarly, we take a line parallel to the first axis, find where it intersects the second axis, and let the coordinate of the point on the coordinate system of the second axis be the second coordinate of the point. This ordered pair is the coordinate of the original point in the plane. Notice that this does not require that the two axes be perpendicular. However, we typically prefer that the two axes to be perpendicular. In this case, we refer to the coordinate system as a Cartesian coordinate system in honor of René Descartes, who was influential in introducing and working with such a system. Note that because the constructions given in this paragraph, we do not have to postulate the existence of a coordinate system for a plane. It's a consequence of the ruler postulate, which guarantees the existence of a distance metric and a coordinate system for a line. So the introduction of a coordinate system for a plane was a major innovation in mathematics historically. It allowed an explicit connection between geometry, that is pictures, figures, sets of points, and algebra, or arithmetic, coordinates, numbers, and equations. And this connection is known as analytic geometry. And these concepts are thoroughly integrated in contemporary approaches to mathematics, as you've probably seen in your pre-calculus and possibly calculus classes. And we can use analytic geometry to prove some results. These proofs take on a much more algebraic feel than other geometric proofs. Now, the history of this relationship between algebra and geometry is somewhat interesting. If we just briefly go over this, geometry was the first type of mathematics that was studied seriously and rigorously without the need for practical applications, even though there are many of them. The ancient Greeks, especially those centered at Alexandria, Egypt, elevated the intellectual pursuit of geometry to an art form. To the ancient Greek culture, numerical computations were done in the context of geometric figures and geometric constructions. When they were thinking of squaring a number, they were literally thinking of constructing a literal square. So all justifications for any proto-algebraic type computations were proved in a geometric setting. Now, if we fast forward a bit to the kind of fall of the Greek culture a bit in the Middle Ages, The most dominant advanced mathematical scientific societies shifted from the ancient Greeks to the Islamic world, Islamic mathematicians and scientists. These mathematicians used Greek geometry to prove some algebraic manipulation techniques. In fact, the word algebra is an Arabic word. The Islamic mathematicians of the Middle Ages invented, discovered, developed basic algebra, what we would call, uh, like college algebra or Algebra 1 or Algebra 2 in high school now. Eventually, this algebra became to stand on its own, somewhat independent of geometry, so that the algebraic computations were performed without reference to formal geometric constructions. Equations were solved without a visual representation. That's a fairly new um, development during that time period. In the 17th century, algebra and geometry came back together through the work of René Descartes, Blaise Pascal, Pierre de Fermat, and a few others. They introduced coordinate system for a plane, now known as the Cartesian coordinate system after Descartes. And this coordinate system brought geometry and algebra back together. With the Cartesian coordinate system, we can graph functions and use graphs to inform algebraic properties of the function, equation, or system of equations. In turn, the algebraic properties inform us about the geometric properties of the graph. Algebra and geometry had once they began become inexorably intertwined. This helped lay the foundation for the discovery, invention, and development of calculus a little bit later in that same century. And note that we've been using a model for Euclidean geometry in GeoGebra. This model really assumes that there's an underlying coordinate system for the plane, and it assumes an analytic geometry approach, at least in GeoGebra. In fact, the name GeoGebra is a mashup of the words geometry and algebra to emphasize this connection. Nearly every object has a geometric representation in a graphic view window and also an algebraic representation in the algebra view window. For example, we can just create a point by specifying its coordinates in the algebra view, and then it's graphed in the graphics view. Or we can simply use the point tool to synthetically create a point in the graphics view, but then its coordinates show up in the algebra view. So these things are connected together. And we have implicitly been using the Euclidean distance formula metric to measure the distance between 2 points given their coordinates. However, once we have the Pythagorean theorem, we see that there really is no other alternative in Euclidean geometry. Can you see why the Euclidean distance metric is a direct consequence of the Pythagorean theorem? Well, it basically is the Pythagorean theorem. Take a look at what we see here. The Euclidean distance metric says the distance between points A and B with Cartesian coordinates x1, y1, and x2, y2 is the distance AB, which is equal to the square root of delta x squared plus delta y squared. Well, delta x is x2 minus x1, and delta y is y2 minus y1. So the delta x is a horizontal change, and the vertical change is delta y. So if you way we can see that is this picture here. If you have a point, something with points x1, y1 here, and a point x2, y2 here, then you can see what we get here. Something's a little bit off on this drawing. That's supposed to be the point 1, 2, which would be 1 this way and 2 up. So it looks like it's off just a little bit. It's been moved up to the right a little bit. The computations seem to be matching what the coordinates are saying, even though the grid's not quite right. Let me see if I can fix that. All right, there we go. That's a little bit better. So this is the point 1, 2. This is the point 10, 7. So how far apart are these points? Well, if we go horizontally over this way, which is going to be the difference in the x-coordinates, from 1 to 10 is a distance of 9. And then we go straight up and down, which is a distance from 2 to 7, which is 5. We can see that the delta x, or at least the absolute value of delta x, is the delta x is the horizontal change. The absolute value of delta x is this distance. And the vertical change here is delta y, or the absolute value is that length. Well, this is a right triangle. So we just apply the Pythagorean theorem to that. And we see that the distance has to be the absolute value of delta x squared, which is just delta x squared, and absolute value of delta y squared is there. Add those two up, and you do a square root to get d. Of course, delta x is x2 minus x1. Delta y is y2 minus y1. And so we can see this works out. So, for example, to figure this d, we just count across this way or do the subtract the x's. 10 minus 1 is 9. Square is 81. And the vertical distance is up 1, 2, 3, 4, 5. Square that's 25. Add that, this 106. So that's the square root of 106. That doesn't really reduce. So that's approximately 10 point something, about 10.3 across there, the distance. So, the distance formula really is the Pythagorean theorem. It's really the same thing. Now, what's kind of interesting about this is we can extend this to 3 dimensions. Look at this one here. Here we have, think of the going from point A to point B across this way, and this is in 3 dimensions. So this is like opposite corners of a little rectangular box, a right rectangular prism. Okay, on the floor or bottom of the box, we could go along this edge from A to D, and that's going to be delta x, or x2 minus x1. Then we go along this edge, that's delta y, which is y2 minus y1, and then we go straight up, that's delta z, or z2 minus z1. Well, if you look at this on the bottom, okay, this is actually a right angle here at D. On the floor or bottom of this rectangle, we go the blue distance this way, the green distance this way. Those are both legs of a right triangle where the hypotenuse is this purple piece here from A to C. So by the Pythagorean theorem, that's the square root of x squared plus y squared. But then we have a vertical right up the side edge here. We have another right angle there at C. And so now we have, this time, this purple is the hypotenuse of this triangle on the bottom, but it's one of the legs of the triangle coming up this way, this kind of cutting across the middle of this box. The hypotenuse is the length we're looking for. Okay? Well, it's going to be purple length square plus pink length square, and then square root. Well, the purple length squared is going to get rid of the square root and just give you delta x squared plus delta y squared. And then you add delta z squared and do the square root. That's going to give you the formula that the distance from A to B is delta x squared plus delta y squared plus delta z squared. So it generalizes that formula in a very, very nice way there. And in fact, you can actually extend this to as many dimensions as you want. Even though we may no longer be able to visualize this, we can say the distance between 2 points in Euclidean n-dimensional space with coordinates, a1, a2, a3 up to an, and b1, b2, b3 up to bn, is basically just the differences in all of these squared and then add them up. So that'd be b1 minus a1 square plus b2 minus a2 square plus b3 minus a3 square plus, and so forth, all the way up to an bn minus an square. Add all those up and then finally do a square root. By the way, Euclidean n-dimensional space is sometimes referred to as Rn, like that. Another important concept in analytic geometry and algebra and in calculus is the concept of slope between 2 points. Okay? The slope is the average rate of change between the 2 points. Okay, so we're going to define the slope between 2 points A equals x1, y1, and B equals x2, y2 is m, is the typical letter we use for it. It's just delta y over delta x. Again, delta y is y2 minus y1. Delta x is x2 minus x1. Now notice I've actually abused the notation here a little bit. Technically speaking, A is the point, and x1, y1 is not a point, it's its coordinates for that point. Technically, we should have a coordinate system C, which is a bijective function, 1-to-1 onto function, continuous function, that maps A points into ordered pairs. And of course, its inverse would go backwards. So really, we should say C of A equals x1, y1, the coordinates of a point A, or whatever x1 is, comma, whatever y1 is, not say A equals x1, y1. But this is just a little bit of a cumbersome notation, and we're going to in this section on analytic geometry, we're going to just just really do this incorrectly, technically, and just abuse the notation a little bit and just say A equals x1, y1. But of course, when I say that, you should think, okay, he's just saying those are its coordinates. So here is something that we have. So again, if we have point A and point B, this way we go to the right, positive delta x, go to the up, that's positive delta y. And here we go to the right, let's see the scale, 1, 2, 3, 4. So delta x is 4, delta y is 1, 2, 3. So the slope is just delta y over delta x, 3 over 4. Okay. You can actually see that 3/4. You can actually see that as a vertical distance right here from this point here up, because when you go to the right one, then the vertical change is the delta y, which is also the slope. So 3/4 would be the length from right here to right here. Okay. Now this also relates to something that we've been talking about in trigonometry and in geometry already, and that is if you look at this angle that this horizontal line makes with the line connecting these 2 points, then you call that angle theta. Well, the tangent of that theta is the opposite side over the adjacent side, which is the slope of that line. So the slope of that line is the tangent of that angle. Now, to get the equation of a line, the slope from any point on the line to any other point is constant. So the slope then would be, if you take a point x, y in general on the line, you take a specific point on the line, x1, y1, then you've got delta y over delta x. You got y minus y1 over x minus x1 equals the slope, and then just solve that for y. Multiply both sides by x minus x1. So you have y minus y1 equals m x minus x1 right in here, and then add y to both sides, y1 to both sides, and you solve for y. So that's called the point slope form of the line. So notice that the slope between 2 points in the equation of the line both assume that we are referencing a given Cartesian coordinate system for the plane. And we can use the results that we have thus far to prove some important analytic geometry propositions. First of all is the midpoint formula. The midpoint of a line segment, M, well, what are its coordinates if you know the coordinates of the endpoints? So the endpoints are A is coordinates, that's 1, 1. The coordinate of B is so the coordinate of A is x1, y1. Coordinate of B is x2, y2. Where are the coordinates of M? I've got it called D here in the picture, but it's M is right there. And so what do you get? Well, so let's prove that it's this coordinate. Okay, so let's start with the coordinate here. Well, if this to get this, you just average the x's to get the x coordinate, average the y's to get the y coordinate. So if this is the midpoint, then what do we know? If those are the coordinates, we know this distance here is well, we got, let's see, it's the average of the distance from here to here. Okay, so if you know this is x1 and that is x2, taking halfway in between will give you exactly x1 plus x2 divided by 2. And the same way for the y's, halfway in between there Well, we just bring these over and we see that that has to be the midpoint there. We can also think of it this way. If we have the midpoint, look over across here and we can see that we have some, we can prove that these are some congruent triangles. These distances for the hypotenuse here and here are the same because it's the midpoint. And then just drop this down and across there, we know the E has the same y coordinate as this, and this one G has the same x coordinate. And we can prove these triangles are congruent. So this distance here and this distance here are the same, so the x coordinate has to be halfway between. And then similarly, this distance from G up to the midpoint and from E up to whatever B, those have to be the same distance, so that has to be halfway in between there. Okay, so you can see that that has to work out. Now, what about parallel and perpendicular lines? Well, it turns out two lines are parallel if and only if they're distinct in the same plane and have the same slope. Okay, of course, that's also obviously in reference to some coordinate system. Two lines in the same plane are perpendicular if the product of their slopes is -1. So here you can see some, and I'm going to see if you can prove this result based on the pictures that you can see. And I've given you some hints to look at some triangles here. So if you could look at this triangle here and this one here, if we could prove that they're congruent, that might help us get some parallel lines here. Okay, because of the angles they make with this, you can use let's see, you can go. It's an if and only if. So if you start with parallel lines, we can get some congruent angles going here. And from that, we can get some congruent triangles, and then that's going to end up giving us the same slopes. On the other hand, if we can get the same slopes out of these, we can prove that these are parallel. So I'll leave that as an exercise for you to work at. Now, to prove that perpendicular, let's say we take two of these. Let's say this one down here, and then this one, this red one going across here. First thing, I think you can notice if one is a positive slope, the other one's going to have to be a negative slope, right? And then notice I've got a triangle here where I went 4 to the right and 2 up. Over here I go 2 to the left and 4 up. And if we can show those two triangles are congruent and look carefully at the angles that are going right here at F, then in fact you'll be able to eventually show that this actually is a right angle. And then you should be able to do the converse. If you start with this being a right angle, then somehow show that that the slopes are going to be, opposite reciprocals of each other, or if you multiply the two slopes, you get -1. I'll let you work on those. So there's some tasks. See if you can write down proofs formally about all these things for the equation of line, slope of parallel and perpendicular lines, and midpoints. And if you study the illustrations I've got, I think you can make some sense out of that. Now, once you have these formulas, we can use these formulas then to prove other results, about other kinds of shapes if we put them on a coordinate system. And so once you have the shapes on a coordinate system, you can use midpoint, slope, formulas, and so forth to help you prove other results. So there's a quick introduction to some analytic geometry.